Hi, in this video, we'll now talk about non-homogeneous linear systems. And in matrix form, you can write it in the following equation over here. So you just x equals to p tx plus gt, where g is this vector in terms of t only, x is your unknowns, and p is your coefficient matrix. So how do we want to solve for this non-homogeneous system? The idea is using what is known as the variation of parameter. So we will look for solutions of the following form, where x equals to the fundamental matrix from the homogeneous system case times ut. So we just sub it in and see whether we can equate it to get anything we like, and we actually get something we like. So ut will equals to the integral of the fundamental matrix times gt. And when you multiply such a ut, it becomes a solution. So we just take an example. Very simply, you got this. We find the fundamental matrix first. Take the inverse. Then u prime must equals to the inverse times gt. Then when you integrate it, you get the following result. So the general solution will just be fundamental matrix times ut and plugging in some constants. So that's it, and very straightforward. If you can exactly see the steps written over here. The idea is now you just use this equation and you're done. So we want to study some behaviors, and one of the most classic examples and systems that we like to study is the nonlinear autonomous system. So we know that if the f only depends on the x and does not depend on t at all, then we say that the system is autonomous. In vector form, it can be stated that the derivative vector equals to just a function in terms of x. So it's written like this. And if this part can equal to 0, then we say that x0 is a critical point or equilibrium solution. So we ask what is the stability of this critical point, and so from our previous examples with the eigenvalues, we see that we define x0 to be the equilibrium solution to be stable, unstable, based on like whether it goes. It's just like the idea is just it will converge to that point, or like it doesn't deviate much away. So that motivates the actual definition for stability, and we say that a critical point is stable if and only if for any epsilon there exists a delta such that if you start near x0 by delta distance, then for whatever epsilon, then as long as your path of travel from that starting point x0 to xt for all t will be less than epsilon. So so the idea is this from the picture. So x0 is here, this is the critical point. Then delta is this. So any starting point in this radius, so let's just say it's here. Let's just say you travel this way only. You fix your travel path. You cannot explode out where it is epsilon distance. So this is stable. This is stable because you just take the distance here. Okay, here. Then you're traveling along here, so you're going inwards. So you're always less than epsilon. So you're done. Stable. But you see, like something like this is unstable because let's just say you have your delta here, so you draw a circle. As you go out of epsilon after a while, so it's unstable. And we say that it is asymptotically stable if it approaches x0 in the end as t approaches infinity. So it goes towards x0. So this is not asymptotically stable because it's just hovering. But if it goes to x0, then it is asymptotically stable. So the idea now is we know what are the stability points, and how do we find the stability points of a non-linear autonomous system? Well, the idea is we must linearize this non-linear system first at each critical point. How can we do so? And why can we do so? Well, if we recall from calculus videos, we see that we can always linearize a point near a point. Then it will just be like the gradient line, right? So, but then near the point, then this fx0 will be like 0. So you only have this, and this is small. The error term will be small. So it's actually this. So, and in two-dimensional case, we also have the following idea. So with the same ideas, we can translate the ODE to the following way. So okay, so you just look at this. You see this, and this. So this is just fx times fy times gx times gy times x minus x naught, y minus y naught. So we just let this be u. Then this u, when you differentiate, is the same as x differentiate. So u prime will equal to this times u plus some error term. And then this error term is super small, so we delete it, and we actually get this, and we call this the corresponding linear system near the critical point. So in general, we say that if x naught is the critical point, then the corresponding linear system is u times the Jacobian times u. U prime equals to the Jacobian at x naught times u, and the Jacobian at x naught is just this matrix sub in x equals to x naught. So let's just take this example, and we see that x prime equals to y, y prime equals to this, f is this, ug is this. So at 0, 0, we first find the Jacobian is this. At 0, 0 is 0, 1 minus 1, 1 minus 1. So this is the system, and for minus pi, it will be 0, 1, 1 minus 1. So this is the corresponding linear system. So this should be pretty straightforward. And now the question comes, what will be the stability? So with this linear system now, we can determine the stability easily. And what can we say about the non-linear version? Well, okay, so let's just do for a 2x2. So for a 2x2, we consider the Jacobian. If this Jacobian has distinct eigenvalues, and both the eigenvalues have non-zero real parts, then the critical point must have the same type and stability as the linear system. Otherwise, it's inconclusive. So the idea is now, you have the Jacobian already, you find its eigenvalues, see whether it is distinct and real and have non-zero real. Then you can say that this critical point in this system will be whatever type, must be the same type in the nonlinear system as well. So why do we have such requirements? Well, because we ignored the error term. So we need the Jacobian to be like, the error term will just be a tiny perturbation of the Jacobian matrix. And this repeated eigenvalue is sensitive to this small perturbation. So we need them to be distinct. The zero real parts are also small to this, well, sensitive to this error terms. So we need it to be non-zero real parts. And this part you can read more in the textbook. Won't go dive into much details. So the phase portrait will be something like this. So in a nonlinear system, all the critical points will look a bit different, but it's okay. The essence is that when you give it a zoomed enough picture, near enough the critical point, this part will all look similar. So that's about it, and that's how you determine the type and stability of a nonlinear system. Yeah, that's all for this video. I hope you have enjoyed it. Please feel free to like, share, and subscribe. See you in the next one. Bye.